Assalamualaikum and good day everyone. So today we're going to cover the lecture week 13. Okay, so today is 9th of June 2021, 11:20 a.m. Okay, so in week 13 we will we will cover applications of Maxwell equation in the explanation of displacement current density. Okay, for Maxwell equation, and also the application of Maxwell equation in good dielectrics and lossy dielectric materials. Okay, so hopefully we will cover this. Okay, this one is all related with Maxwell application. Okay, application, Maxwell equation application. So in Sadiku book you may refer starting from page 439. Okay, so before that let me refer to the one of the page in Sadiku book where actually shown us the Maxwell equation list. Okay, so if you can see at page 445, okay, at page 445, so we can see there is 4 Maxwell equation. Which one? This one is in the differential form and this one is in the integral form. Okay, sorry. And we have also this one in the point form. Okay, so let's say for this one is your first, right? Your first Maxwell equation, where is actually your divergence of D equals to rho V. Okay, then the integral form is the D dot ds rho V dV. Okay, this is your Gauss law. Okay, so this is all the Maxwell equation that you learned. Okay, we specifically the one that we will look for our displacement current that we will learn later on is actually this. Okay, where is the curl of H is equals to J plus the differentiation of D over dt. So this one is known as displacement current density, and this one known as the conduction current density. Okay, J and D over dt. Okay, so let's really head back to the page that we should start our lesson today, which is on the displacement current, page 439. Okay, so I put this away so to save up space, and you guys may refer to the slide as well. Okay, to the slide, and like I say, if you found any this conflicting information, do let me know. Okay, so we learn from the continuity current equations. Okay, where you have divergence of J equals to negative rho V over dt. Okay, this one is your continuity equations. Okay, so let's imagine our one of the application, okay, where we're going to justify the existence of displacement current density. Is that, let's say you have a capacitor, okay, then you have a current which is varying with time, and passing through this capacitor you also have the current with time varying components. Okay, so okay, if you can see here, the formula that we use, okay, later on it cannot, the conduction current density cannot satisfy these situations, okay. So we need to add something to modify equation, okay, based from our static field that we learned before. We need to modify in order to suit these conditions, okay. Okay, continue. From our continuity equation, we know that divergence of J is equals to negative d rho v over dt. Okay, then we also know that, okay, if we were to put divergence, okay, divergence of this one, J is actually divergence of H. Am I correct? It is a curl of H, which you will have negative rho v over dt. Okay. Okay. So this is your conduction current density. Okay. So if you see divergence of J, then we expand it because this J is actually equals to curl of H. So we just put it in. However, from the identity that we learned from the mathematics, okay, we know that divergence of curl of any vector, okay, for example like this, will result in 0. Okay. So if we were to describe this, okay, as 0, then, okay, for this one, if we were to relate, this one should be 0. Am I correct? Okay, should be 0. However, if you notice something is not correct, okay, something is not correct where this one, if you see, cannot result in 0. Okay, so we need to do some modification, okay, to suit these situations, okay, where we need to modify our equation that we learned from the static field, okay. So we need to introduce another components, okay, to make this question valid, okay. So we add rho v over dt, okay. So now it's valid, okay, because this one plus this one will result in 0. Am I correct? Then further expand, okay, we further expand these equations, okay. Negative rho v over dt, we know it's a divergence of J. Am I correct? So okay, we just do some rearrangement, and this one's rho v, taking from the formula that we learned before in your first Maxwell equations, okay, which is divergence of D equals to rho v, okay. So you do some replacement, okay, substitution, okay, then you came across like this, the expanded form, okay. Now, okay, I'm transferring here to save the page, okay. If you see, if you want if we want to take the common component out, okay, we take the divergence out, okay, simple thing here also, we take the divergence out, okay. If you take the common out and you only focus on the differences, then you will come across that curl of H is actually J equals to d over dt, okay. So this one is the conduction current density, and this one is a displacement. Okay, so if you notice this J, okay, have a time component, and this one is actually the displacement current density. So if we want to make a proper labeling with this will be your JD, and this one will be your JC, okay. Sorry, this one is your JD because it's displacement, and this one is your JC, okay. Sorry for the error. So this is your displacement current density, and this one is your conduction current density. So what happened in this situation, okay, there is a gap where you have a perfect, you can have a dielectric, whether it's perfect or not is depend, okay. So we have a dielectric. So where this is dielectric means that the conductivity is supposed to be 0. This one is for the perfect case. So this one is actually a dielectric. Okay, in the case of, let's say, perfect dielectric, we have a conductivity of 0. Okay, so what happened is that when the current passing through this parapet capacitors, so we still have a current flow even though we have a perfect dielectric here. Okay, so what is actually current flowing through here is actually our displacement current density. Okay, so this displacement current density is actually, you can relate with the everyday life application. For example, we want to transfer signal from point A to point B over wireless connection. Okay, one of the wireless medium that we have, and you also know that this is air, open air. This is a medium which is a dielectric. So this is how we make use of a displacement current density in order to transfer our signal, okay, from one place to another over a non-conductive medium, which is dielectric. For example, air. Okay, just like your wireless signals. That's why we're able to talk over the phone. Okay, because we make use of this displacement current density. Okay. So this is the equation, okay, that I rewrite again about relating our conduction current and our displacement current. Okay. So, and we also know that actually this our conduction current density, okay, conduction current density JC is, when we want to relate it with the conductor, it is JC equals to sigma E, okay, which is your conduction current density. And how about your JD? JD is actually, you can, just like what we can see here, D over dt. You also know later on, right, we can relate this D with your sigma E. Am I correct? Okay. So time varying magnetic field produce time varying E field and vice versa. Okay, if you have this with varying with time, of course your E will vary with time, your I also will vary with time. Okay, this is and vice versa. So both conduction and displacement current are produced in time varying field. Okay, they are produced in the time varying field. So application of this, we can apply this in a good dielectric material and lossy dielectric material, which we will see later on, inshallah. Okay, so in good dielectric material, good dielectric material, so your sigma it should be 0. Okay, and for lossy dielectric material, your sigma should be not equal to 0. Okay, this one is for good dielectric material, which is usually expensive. Okay, in lossy dielectric material, we have also this our sigma. How we have this sigma, it is not equal to 0 because it's not a perfect dielectric, it's a lossy. However, it will have a small value of conductivity. Okay, so let's see from our page 439, which discuss about displacement current. Okay, okay, so you can read from this all along, and then this is, then we look into this. Okay, we see. Okay, here, based on the displacement current density, okay, based on the displacement current density, we define the displacement current, okay, as, okay, here, ID equals to JD ds over ds over d dt of your ds. So this one is your ID is equals to integral of s equals to your JD over ds equals to integral of surface d over dt and your ds. Okay, if you see this JD is it here, right? You can see this where we just do some expand. Okay, and ds is still ds. So this is also one of the equations that you need to familiarize with. Okay, and then in the Ampere circuital law, if we learn from the previous lecture, okay, the one that we learned from the magnetostatic field, okay, the unmodified equation valid for magnetostatic, we have closed integral of h dot dl, okay, vector h dot vector dl equals to surface integral j dot ds, which is equal to our I enclosed, which is I. Okay, so where I is the current through the conductor and S is the flat surface bounded by L. Okay, this one, as you all know, is depends on which lines or which surface we are referring to, and we apply the appropriate coordinate to settle it. Okay, to solve the question. So without further ado, I hope that I will not have memory problems. That's why I a bit fast in giving lecture. Okay, so now we try one of the exercise. Okay, one of the exercise which is here is the practice exercise 9.4. Okay, okay, In practice exercise 9.4, it given that in free space, okay, it mentioned here in free space. Okay, in free space mean in free space what happened in free space means you have this one. Am I correct? So in free space, E is equal to 20 cos omega t minus 50x